this programming, there's one other thing in the area of sort of news I wanted to mention, Easy Capture the Flag. Easy Capture the Flag was supposed to start today. It's going to start March 13 instead. This is what happened last year. They were a whole week late starting because there's incredible interest in this. I highly recommend this. You people in this class are at the right level for this. This is a high school hacking competition, and it is not any too easy, but it's easy enough for us. Capture the Flag. If you've never done them, this is the right one to start with. And if you come to Monday at 5 p.m., I'll be at the CCSF Hackers meeting to get people started on this. You form teams of up to 5 people, or you can work alone. You can work from anywhere. It's up for a whole week, and it's just a bunch of puzzles to solve. And there's a scoreboard. You're competing with other people. There's cash prizes, but you only get them if you're really a high school student. So we're technically observers or something, but we're still allowed to compete, and you can see how well you do. And you really should get it started with Capture the Flag competitions. Anybody in security should be doing these. They are very popular. They're a lot of fun if you find one at the right level. The most common problem for beginners is they're all too hard. Everybody, you look at them, all the puzzles are impossible, you're not learning anything. This one does not have that problem. There are ones that are easy. Some of them are easy, so you should be able to solve at least a few of them if you're in 120 or 123, using the techniques you've learned in the projects in the book. And then they go all the way up to really hard ones, so you get to be challenged. And so I highly recommend it, and it's worth extra credit. So come to that event on Monday or sign up. Find a link on my page and give it a shot. You get extra credit for trying, you get more extra credit for any problems you solve. And you should all be able to solve at least a few of these, because they really aren't kidding. They start out easy. You probably, if anybody, you're very unlikely to solve them all. I never have, but you should be able to solve some of them. Anyway, so let's take a look at programming. A lot of students studying security, and some security professionals don't know any programming at all, and that's no good. As a visiting speaker, Muscles was here last week saying you really should learn a professional level of coding, which is more than a lot of people recommend. But anyway, you should learn some coding, and the more the better. If you don't know any language at all, the first language to start with is Python. That's what it's there for. Python is very easy to do simple things in. It is in fact a very advanced language that has object-oriented code and everything else in it, so it can do pretty complicated things, but it is possible to use it to do very simple things, and it's the right place to start. Either Python or JavaScript is the right language for the very first language you learn, because they are very easy. And then, if you want to make something like Microsoft Office, you have to use a much more powerful language like C++ or Java. But you start with a simpler language. What's that?
Java's like the only one I know pretty well.
Yeah, well, Java is in fact quite a complicated language. It's complicated as C++. You have to compile things, runs. And so if you know Java, then you know a lot of programming, a lot more than someone that just knows Python. But Python is much simpler. But yeah, I started back in the ancient days with BASIC, and then Fortran, and then C. And once you've learned one, it's very easy to learn more. They're all basically variations on the same theme. Anyway, so the basic concept of programming is actually what they call NP-complete. Mathematicians up in the level of abstraction, where it is essentially philosophy, have figured out that there is a category of problems that can be solved by a computer, and that is what's called the NP. And there's a P is NP, I forget. Anyway, which means anything where there's a series of steps that is clear, and if you just follow these steps, you'll get to the end. A computer can do that. There are other things that do not have any known series of steps that lead to the end, and computers can't solve those problems. And there is a huge philosophical debate over how many problems in which category, and whether one set is really bigger than the other. Anyway, that's why all programming languages are sort of the same, in that you can do anything in any language. The only reason, and so when I started in the 70s, there was a debate. There were maybe half a dozen languages at that time, Pascal and BASIC and Fortran, and people would argue about which one would win, and all the others would go away. Just like in the meat world, English pretty much won. Every other country pretty much has to learn English. We pretty much standardized on it. A couple centuries ago, it was Latin. Everything was written in Latin, and everybody had to learn Latin. But that did not happen at all in programming. There are hundreds of languages in active use, new ones coming out all the time. Web developers in particular typically know 30 or 40 languages and use them all. It's crazy. It has turned out to be the case that even though every language is mathematically identical to every other, in fact, certain types of jobs are easier in one language than another. So it turns out to be worth it to make a specialized language for each type of job. Anyway, we'll talk about a few things here. So here's the basic rule of computer programming. You have to write code The code has rules. You have things you have to have semicolons and spaces and parentheses and stuff in the right place, and if you make any mistakes, the computer will reject it. At least serious languages will reject it. There are some languages, like HTML, that will forgive your mistakes and try to guess what you meant, which is kind of unbelievable, and that's what makes browsers very big, and that's what makes HTML very buggy. So HTML is the only language I know that has the property that you can write a page, and people can look at it in 5 different browsers, and they will not see the same thing, which is strange and bizarre. But HTML is not even a programming language, it's a markup language. Anyway, the fundamental thing that makes a programming language is branching, looping, and testing. Those are the 3 things. Now, you can have if you have those features, you have an NP-complete language and you can do anything, but it turned out to, and when I started, this is how I did it in Fortran, you wrote spaghetti code. You just write page after page of code, and then you want to do something, you go to down here, then you come back with a go to, and pretty soon the flow chart just looked like drunken spiders had made it, and it was very hard to upgrade and maintain. So people went to structured languages where you can define a function, and a function does one specific job and then comes back, and you write each function separately and test it, and then you just plug in the function modules, like you might plug in whole circuit boards into a motherboard to get the job done, and that turns out to be much more effective at making code that works and that can be expanded and maintained. So branching takes you from one part of the program to another. There's some way to stop doing something up here and go do something down here for a while. Looping is doing something over and over some certain number of times, and testing. Test some condition to see if it's true or false, and can go one of 2 directions, depending on whether that condition is true or false. Those are the 3 logical things you must have in order to do programming. So the simplest C program here, C is a structured language, and it is quite difficult, actually, but you can do, if you just want to print hello world, you have to put a lot of boilerplate around it. This is what includes the standard I/O libraries. By default, it doesn't have the ability to print, which is kind of crazy. So you have to include the library to have print, then everything has to have main, which tells it where the program starts, and you have to have these curly braces in it, and you have to have the quotes match, you have to have the semicolon, you have to have the parentheses match, and the curly braces. If any one of those punctuation marks is missing, it won't work at all. And I ought to mention, let me get my virtual machine up here. I think, yeah, this class, in fact, this project, going with this stuff, got hosed for some students by a failure in the latest Kali Linux. And yeah, this is the one that's been updated. Let's see how far we can get. Some students were using a machine like this. If you perform the online updates on the latest version of Kali, you destroy it. They have messed up GCC quite badly, which is a pretty extreme thing to mess up. So let's see what I've got here. Okay, let's do hello.c. So it's include pound, there goes there. I think we're going to get my slides. Yep, okay. std.h main. This, by the way, is a good practice. Whenever you have some opening punctuation mark, put in the closing one right away, and then go back and fill in the middle, so you always have a pair. And so it's printf. Hi. Oops, I messed it up. Thank you. Yes, good. And then let's put in a /n to make the carriage return. Okay, so that might work. Let's see if it does. You compile it with GCC. GCC is GNU compiler. You tell it where to put the output, which in Linux is typically the name of the thing without any extension, and then the input is the file with C code. And okay, it gives me a warning. Now the warning tells me I did not specify what variable type the main routine was. If the main routine was a subroutine that was going to return to something in my program, it could return a value. And I didn't tell it what kind of value that would be. So it isn't just a warning, it doesn't stop it from running. It's telling me I've done something sloppy and unrecommended, but not fatal. So I run it with hello, and it prints hi and doesn't crash. So that's nice. Now, let's expand this one. In the project, you go up to hello2 and hello3. So let's copy hello.c to hello2.c and nano that one. Okay, So now I'm going to take input from the user. So I'm going to define a character variable, name 10, and then do scanf, %s. I think I just put name, or do I put a pound before? I think just name will do it. We're going to see. Yeah.
So for scanner for C language,
Yeah.
it's scanf. It's not like Java where you have set scanner, where you have scanner, set scanner, and you make your declarative and whatnot.
It's a little easier.
It's
Yes.
a little better.
Yeah.
It's much
Yeah.
easier.
You can do IO to a file, and then you'd have to open the file and get a handle and use fscanf and put the handle here. But yeah, like I say, Java is one of the more complicated ones. If you know Java, the rest are often going to seem easier. And so name, all right, that might work. Let's see if that goes. Then I want to compile it the same way, except it's hello2. Whoops, that's copy. GCC, there's the one I want, hello2. And I got to do it right there. All right, good, just a warning. So hello2 runs, and I can put in Sam, and it says, hi, Sam. All right, that's what I wanted to get there. And this also introduces the most common problem of C, which is the buffer overflow. If your name is long, it crashes with a segmentation fault. So this was the most important security vulnerability. It was the first one people learned how to exploit due to an article in Frack almost 20 years ago by Aleph Null. And for 15 years, this was the main way you took over computers, because people would write C code and they would forget to limit the input to the size of the container. And this is entirely the fault of C. Let me copy hello2.c to hello4.c, and we'll play with this. But let me just cat hello2 to talk about it. So what had happened here is I defined a variable that only has room for 10 letters, and then I input from the keyboard into that variable without limiting it to 10 letters. So you could put in 40 letters, and any sensible language would not do that. Visual Basic would not do that. If you try to put 40 letters in something that only has room for 10, it will automatically reallocate a bigger place to put it, which means it's a more complicated compiler, a more complicated runner, and it consumes more memory and processing time when you run it, but it makes it much safer. C will never do that. C will always do exactly what you tell it to do, no matter how stupid it is. And so you set aside room for 10 characters, you put in 40, it says, yes, sir, you must know what you're doing. I would never question your wisdom. It does whatever you say. All right, so let me, I'll get back to that. Anyway, you can put comments in with /* and other syntaxes. This is a really important thing, because if you write code, you will find that when you look at it a week later, you can't remember what you were doing or why. I've even had brilliant ideas in written code, and I get up the next morning and it's just gibberish, complete drivel. I say, I don't know what I was thinking. Just imagine a company with 100 programmers trying to, people are coming and going, and you're looking at something that some guy that got fired last year wrote and trying to figure out why it's not working. This is pretty miserable. I know several large companies have just given up on this, and they said, always just rewrite the whole thing from scratch, because it's so painful to figure out what somebody else is thinking. It's similar when I'm up in the lab and students are doing projects and they get hopelessly lost, and you have to figure out, wait, 10 steps ago you went off the track, and how did you end up in this strange place? It's tough. So serious programming companies have a requirement that you must document your code. You must write pages explaining exactly what you're doing, and they'll fire you if you don't, because they learned the hard way that if you don't have really clear explanations, nobody can figure out what you're doing and maintain it and update it as time goes on. So here's branching and testing. You can define an integer variable, scanning the age. If it's greater than 0, it prints something here. If it's not greater than 0, it won't print that. So this is branching and testing, and this is what we're going to use to take over machines in the exploit development class. So we start in the main routine. You have the operating system. It jumps into main. Then you go down here and print something, so it stops processing instructions in main, and it goes down to printf and prints them, and then when it's done, it returns. Then later on, it decides to go to scanf to read something from the user, so it jumps down to the scanf routine and then comes back. This is a vulnerable point of code. What happens is, just like you're doing your homework and the phone rings. Then you have to stop doing your homework, go answer the phone call, do something else, and then come back and pick up where you left off. But maybe you forgot where you left off. That's exactly what happens to your computer. You're in the middle of main, you're down to this, you've done this command, you're down doing this command. Now you have to save your current state. What line was I on and what was I doing? Stop doing that, go to some other routine and do something different. and then return to resume where you left off. So there is a data storage item called the stack frame designed for this. This is why the stack exists. When you call a subroutine, your current condition of the processor is pushed onto the stack, and you make another stack frame above it, which is used for temporary storage while you're down here. And when you return, you stop using that stack and go back to the previous one, which hopefully has enough information to resume where you left off. The problem is, if there are buffer overflows in this routine, you can write a variable and go right out of your stack frame into the next stack frame and corrupt memory, so that when it tries to come back, the record of how to resume has been altered. And instead of resuming where it left off, it resumes somewhere else, and you take over the machine. It's very powerful, and it's the heart of all memory corruption vulnerabilities, which is the most common type. A whole lot of defenses are built into operating systems just to stop these buffer overflows, and they cause buffer overflows to be less common than they used to be, because they're harder to exploit. But the leader, at least around 2012, was now dangling pointers, which amount to the same thing. There is a way to write to memory in an unexpected location and alter things that were not supposed to be altered. So here's looping, yeah.
So, would it be safe to say sometimes that if you get a memory read address error,
Yeah.
that's because of it being exploited from something you may have downloaded, so it's a key generator?
Yes. What happens is any errors in how you handle memory can lead to this. Now, in fact, most crashes are not exploitable. They do something like fill up all memory and hit the end of the stack and then give you a memory error, but that's not exploitable. Maybe 1 in 10 of them can actually be exploited, but you don't know that. So, I mean, all these things start as crashes, and then a very careful, that exploit development is the process of taking something that crashes and analyzing it and figuring out how to use it to take over the machine.
Okay.
Yeah. All right, so looping. When I began, there was this very primitive language called BASIC, which is now extinct, although Visual Basic is its ancient cousin. And in BASIC, if you want to do something 10 times, you wrote for I equals 1 to 10, print I, next I. That was how loops worked in BASIC. And you never had any problems with this. It was real easy to tell it's going to do it 10 times. For some ungodly reason, BASIC went extinct, and we went up to languages like C. So this is how you make a loop in C. You define an integer variable, then for the starting condition is I equals 0, the test is I less than 11, and the increment is I plus plus. So let's take some votes. How many times is this going to print that line? 10, that's one vote. Any other votes? 11. Any other numbers? The correct answer is 11. Let's try it. This is another whole category of vulnerabilities, again, brought to you by C. C is the language that creates most of the vulnerabilities we're exploiting, because it is not written in a way that's easy for humans to understand, so everybody makes mistakes, even professionals. So let's make a loop.c, include stdio.h, main. Okay, and so it was int I for I equals 0, I less than 11, I plus plus. I'm going to put an I in here so we can see it. Okay. There. So now we'll see the number. And there. That should do it. If it'll compile, if I didn't make a mistake, oh, I'm missing semicolon. It won't let me do that. All right. So let's see if this will compile or what. Loop dot.
Missing an opening parentheses.
Did I mess something up?
Between print and I.
Oh, you're right. I thank you. Good. Let me see what I thank you. All right. That would be a crash. I do need to put that there. Good. All right. Thank you.
Is it a print F or is it a print?
Should be a printf. Did I put print? Oh, thank you. Good. And another space in there too. Good, good. All right, so let's try that. So GCC loop. Okay, good. Loop. And there you go. It prints the 0 and it prints the 10, so there are 11 of them. That's the problem. It is very annoying. And unless you have strict standards, you will go out of your mind, because you could have, whoa, not that one. By the way, if you do try to print machine code, that's what you see. Drivel, that's hard to read. That's the compiled version. The only thing you can print reasonably is the source code. All right, so it's going to start with 0. It's going to keep going as long as I is less than 11. an increment every time, so it's gonna print 0, it's gonna print 10. When it hits 11, this is no longer true. But you could use less than or equal to, and that would have a different result, and on you go. This is the off by 1 error, and there are a bunch of vulnerabilities based on this, where people try to do something a certain number of times and they end up accidentally doing it an extra time or 1 time short, and that's often a vulnerability you can take over a machine with. There's another similar one, by the way. If you increment an integer variable and make it bigger, 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 it's really stored as a binary variable. It's only so long. And binary variables make negative numbers by putting a 1 in the most significant bit. So if you just keep adding 1 to it long enough, it'll get so big, it'll turn into a negative number. So there are examples of exploits where someone doesn't want you to put in more than 100 characters, but they use an integer variables. So the way to take over the machine is to put in like 100 million characters, because that's so large, it will be interpreted as a negative number and pass the test that the length of the variable is less than 100. That's an integer overflow, which is different logically, but ends up having similar consequences to buffer overflow. You can sneak in stuff right past a condition that was supposed to prevent it. So an algorithm is what specifies the steps you go through to make your task, to do your task, and a bug is an error in your code that causes something to go wrong. You can write your code in pseudocode. Pseudocode is commonly used, especially in malware analysis. If you have an executable binary and you don't have the source code, there are decompilers like Hopper that will turn it into pseudocode. They can't make it into real code that would compile, but they can make it into code that lets you understand the logic. So if you want to make lunch, this is the plan. Purchase ingredients is the function that's going to call get car, drive to store, which are sub-functions. Then purchase these items, then end the purchase. This is the kind of logic that you have going through steps. And especially now that we're going to have those self-driving cars, people are currently arguing very heavily about the logic of you are driving, it is raining, there is ice, you detect a person in front of you and a crowd of people waiting at the bus stop, you don't have time to hit the brakes, who do you kill? Humans make this decision, and the problem is when humans make this decision, they can then take each human to court and decide them. Now they have to write an algorithm which will program it so the programmers make a decision of who to kill. And so who do you sue and who's liable? People are currently fighting this one out. Now, it's the same thing as ever. There's a certain number of accidents and people get killed, but now we have someone to blame for it, rather more than just the driver. Anyway, and then you have all the other stuff too. What happens when they're in mistakes and kill people? What happens when people hack into the car and make it kill people? Anyway, so you have to document your stuff, like I said. Typically, the people that enjoy programming hate documenting, and they have to be forced to do it by their boss. There are a lot of bugs in code. There's an industry standard of 2 to 3% bugs, which is unbelievable to me. I'm not aware, anyway, Linux is much less than that. Windows is much less than that. The entire source code for Windows 2000 leaked out, and it was an embarrassment to Microsoft because the comments are very foul and blasphemous. It is very frustrating to work on a huge project like Windows or Office. And I remember one of the comments was, I now have to write 2,500 lines of complete shit because the other department will not obey the standards when writing their device driver, and I have to do it here. And, that's the way it is. But many, many foul complaints in Windows 2000 as the teams found each other frustrated by other teams not doing their job. And Linux has very few bugs. Microsoft did much less than that. But still, that's a lot of bugs. Like I say, most of them just cause some minor problem, but some of them are holes you can take over the machine through. And Microsoft explained that if you use any version of Windows before Windows XP Service Pack 2, it is so full of bugs they will never get it cleaned up because none of their programmers even knew about security issues at all at that time. Their official policy was to ignore security problems until 2002, and then they developed a book and made all their programmers read a book called Writing Secure Code, and they rewrote Windows XP entirely. And until then, their programmers didn't even know what a buffer overflow was, which is the way we're still pumping them out at this college. All training programs I'm aware of that train people to code will produce programmers up to Microsoft's 2002 level that do not even know what the typical errors caused by their language are. All they know is how to get things done fast and make them look pretty and subject them to normal quality control tests. Security is left to a second team, which would be us. So anyway, C was invented in '72. This was a big leap forward for computing. Back in the '70s, I was in the game, and you would buy a mainframe, and every mainframe had its own language and its own operating system. So you'd buy a computer for $1 million like at Amdahl, you'd get about 8 phone books full of documentation, and you would have to learn how to run that mainframe with its language. And if you had an IBM, nothing was the same. And this was crazy, and some dreamers wanted to create this thing called the internet where the computers would actually talk to each other, and in order for that to work, they'd actually have to be speaking the same language. So they developed the language Unix, and they developed C to be the language that was used to write Unix. And then all you had to do for every computer was write a C compiler in whatever their goofy language was, and then you could put Unix on it, and now they could all talk to each other, and you'd have code on one machine used on another machine, and that was the huge leap forward. So that started out at Bell Labs. Bell Labs was funded by the government, and the rule was that Bell Labs was not allowed to trademark and charge money for anything created in this program, so that's why Unix was free and C was free, because it was paid for by the government as like a research project. Anyway, what's really used inside every machine is assembly language. Assembly language is just a bunch of binary, and that is matching the hardware built into the processing chip. So each chip is different, and in order to make binary a little easier, you can see it in the form of assembly code, like what you've got here. This is one notepad in Windows, disassembled. So here's the start. Here's a push 70 hex onto the stack. That puts those 8 bits on the stack. Then you push some offset of some routine on the stack. Then you call something at this location. Then you do an XOR and a push and a move. And these little instructions that are hard to understand at first and confusing are what does all the work. And it takes hundreds of lines of this to do anything reasonable, like open a window and show some text and such. And this is stuff, you can learn it here. We now have a good assembly language class. Several students have taken it, and it's very good over there. Assembly language is very important for malware analysts and reverse engineers because you get a finished product and you don't have the source code, and you have to figure out from this what it does. And we're teaching that here, but very few people actually write things in assembly language because it's so difficult. It's what they prefer to do is write it in high-level languages like C or Java, and then the compiler turns it into machine language, and you don't mess with this directly. But if you want to do hacking, you often have to get down to this level, and this is what the DEF CON capture the flag is exclusively about. There are many aspects of security, but the one aspect that they focus there is this binary elite hacking. So they develop basically new viruses and new defenses right there on the spot and take each of the machines over with it, all down at this level. And there are people, I know a guy named Joseph Slack who works at a company, and all he does is look at this all day long. The tool for this is IDA Pro, costs $6,000. It's like Photoshop. You have to study a lot to learn how to read it, and then you just nothing but read this stuff all day long. Yeah.
Is there like any tools like such IDEs for assembly language to make it a little easier?
As far as I know, there aren't. There's debuggers, because coding stuff in assembly language is kind of weird. What you're usually trying to do is understand code that came in that form.
Right.
And so at least where I am, it's the other way. There may be some IDE to help a little, but it won't help much, because why don't you just use a high-level language if you want it to be easy?
Right, I understand.
Yeah,
There's
yeah.
too many zeros and ones to try and remember.
Yeah. Anyway, but yeah, go ahead.
Is it a decompiler for assembly?
This is a decompiler, yeah. That's what decompilers do. Decompilers take machine code and turn it back into something readable, but usually they can only go this far, turn it into assembler. Now, as I mentioned, there are some like Hopper that will actually turn it back into pseudocode, which looks kind of like C. But that's only to help you understand it. It's not really accurate. It won't compile. Android apps can easily be reversed into Smalley, and Smalley is almost as easy to read as Java. So Android applications are all very vulnerable, much more than iPhone applications, because iPhone applications are written in this kind of language, and if you try to examine them, it's this hard to read. But Android apps are all distributed with readable source code built into them for all practical purposes. So you can very easily go in there and see what they're doing. And the developers typically do not know this. Yeah?
I thought they were I thought Apple had its own language, like Apple Swift, I think it was called.
For native code. But the apps that third-party people write are written in Java and compiled down to Smalley, which is bytecode, which looks very much like Java, and it's almost as easy to read. So one very common mistake is coders will put secrets in their code, like hard-coded passwords and such, because they assume, since they don't distribute the source code, nobody can see them. But it's not that hard to see, especially in Java. Anyway, so the compiler is the program that takes that source code written in with things like main and integer and turns it into machine language so you can run it. Ubuntu Linux actually does not include a compiler by default, which is kind of nuts, but you have to add it by apt-get install build essential, which I found pretty frustrating at first. Anyway, we've done the hello world, the comments we've talked about. The include statement is how you include libraries. Almost nobody wants to write an entire program. You want to include libraries to do boring things like write to the disk, write to the network card. And so you just put include statements at the start of your code, and then you can use somebody else's library. This, of course, is both good and bad. It's good in that you can focus on the part of your code that's special to you and not do all the difficult, boring work of writing libraries. The bad part is the libraries themselves have bugs. And this happened to Apple iPhones about last year. There was a major bug in one of the networking libraries, so it could be fooled into accepting an invalid HTTPS certificate. And that affected something like 15% of all the apps in the store when that came out because they all used the same library. So, it's in Windows, there's another big vulnerability. The libraries in Windows are dynamically linked, which means if I have one program like a browser that does network I/O, and then I have some other program like an email client that does network I/O, it only loads one copy of the networking library in memory, and they both use the same one. So it's kind of unsanitary. Many of your codes are sharing one library, and they can alter it or load a corrupted or malicious library and fool another program into using it, and that's how most attacks work on Windows. You trick a program into loading the wrong library, or you corrupt the library somehow, because then you don't even have to find a vulnerability in the code the company wrote. You add extra code to it, which is giving it the malicious function you want. That's dynamic linking. Of course, the reason Microsoft does it is it makes programs load faster and consume less memory, because if 10 programs are using the network, they don't have 10 copies of the library, they just have one. So it boots up faster, your program is launched faster, and they run cleaner. They run faster, but it does introduce a vulnerability. Yeah?
Question, but I remember last class you mentioned Windows developed the ability for certain segments of RAM to not be executable or not
Yes.
be writable over.
Oh, that's actually implemented by the motherboard.
Okay.
The NX bit, and Microsoft did include it in their modern versions.
Yeah.
That's
so
NX.
It seems like that problem would go away then if you can't write to these like shared library.
Yes, but they're not made non-writable.
Okay.
Although usually it's write or execute. Yes, these days that would help prevent it, altering it. However, to overcome this, all you have to do is call the function that changes the permissions on that part of memory.
Mm-hmm.
And that's pretty easy to do. So, but you're right, that's another barrier. It's a good point. All right, so you got functions. Functions, like main is a function, it has parentheses, has curly braces around it, and every program has to have a main function because it has to know where to start. You can call other functions, and you can call them as much as you want. Doesn't matter, you can have functions call other functions. That's why the stack exists. Until you run out of memory, you can go very many layers deep. You can declare your variables. You have to declare them by type. So this is an integer. And let me make this higher on the screen and smaller is the best answer in a room with this kind of projector. All right. So in C, you have to declare the variable types before using it. That's part of what makes it a structured language, which is confusing to people who start with other languages that have weak structures, like, say, PHP. But you define this to be an integer, and that tells it it's a number, not a letter, and how big it can be. So you've got integers, floating point, double precision, characters, strings, various kinds of variables. Everything in the computer is just the same kind of binary code, but the C can interpret it different ways. So I++ here adds one to the variable, and you can add things, subtract them, make things negative, increment them, divide them, do modular arithmetic. Every kind of arithmetic is, of course, supported on all these numbers. So you can do graphic displays and rotate things in 3 dimensions and such. You can do logical things like see if I is less than or 11 or not. And you can see if things are equal, not equal, greater than, less than, greater than or equal, less than or equal, and all that. This can get you in trouble. In PHP is what's called a weak typing language. So you can set A equals 1, and it will decide A is an integer. Then you can set A equals apple, and it will say, oh, it appears to be a string now. It will just convert it to a string without telling you anything. So you don't really know how it's interpreting variables, and that means there's equals, which assigns them. So A equals 1, it'll put the 1 in A. Then there's A equals 1, which will be the question, does A equal 1? with weak typing. And then there's 3 equals, which mean are these things identical in type and content, which can get people in a lot of trouble. In our web development, web hacking class, there's a demonstration there where you can actually log in with the wrong password because the programmer used 2 equals. And if you put in a password that is an unexpected variable type, like you put brackets around it so it turns into an array, it's now not equal to anything. And the answer to the comparison is always 0. And with certain code constructions, that means that password will always be accepted. This is a common problem of fail open, where there's a test for some security purpose, and if you manage to confuse the test, you can get through with something that does not match. All right, so the buffer overflow is the one I just showed you before. If you set aside a certain amount of space and you accept input without limiting it, C will permit you to put in too much and it'll crash because you override the memory that was reserved for this purpose and you corrupt other memory until you hit something important like the stored instruction pointer, and now it's going to try to execute an instruction in some ridiculous place and crash. So here is how buffer overflows work. This is a simple explanation of it. You have memory. You have a large block of memory, and you have a stack frame here. You put name for 20, then you have other variables, then you have registers, and down here past that you have the stored instruction pointer. This should actually be a row lower, but the point is, if I'm able to override the name, I can have a long name, junk, and somewhere down here is some code that controls the instruction pointer. So when it returns from this routine, it tries to pick up where it left off, but I have changed this number, so instead it jumps down here. So what you do is you inject not only 20 characters, maybe another 50 or 80 to get down here, you inject another 100 or 200, so you add a bunch of executable code down here, all in the name. You put in no operation, no operation, no operation. That's a 90 hexadecimal command that does nothing. And you might think you don't need a machine language instruction that does nothing, but it's just as important as the 0 in numbers. It does nothing, but that's a valid execution that goes to the next line. So I put in maybe 100 nops, and then I put in the egg. The egg is the active ingredient of my exploit that does whatever I want to do, like change the administrator password, or most commonly, make a network connection back to me so I can execute commands on the server, arbitrary commands. Your goal is to execute this egg. So you take something like a name and you put in all this long stuff in the name. And now, if you do it right, you figure out where you are in memory, you put that number here so that when it tries to return from this function, it will go here, hit your NOP sled, slide down the sled, nothing, and then execute the egg. That's how you make buffer overflow exploits. And they're very effective unless you have some defense to stop them, and so modern operating systems have a lot of defenses to stop them. The simplest one, well, one of them is address space layout randomization. In the early days, like MS-DOS and Windows 95, you would just use your memory. Windows would load starting at 0, then you'd have your antivirus load, then your IIS on your server, your SQL server, whatever program you run would just use the next available memory. So it was very easy to figure out where you were in memory because you could just build a copy of that server of your own and just figure out pretty much where things were. In order to prevent this exploit from working, address space layout randomization, just every time you reboot, it picks a random location in memory with everything. So you don't know where you are. You could be anywhere. And therefore, it's harder to find the code once you inject it. This did slow down people for about a year or two at the Canada Pwn conference, which is the hacking test of this. They have a conference there every year where they bring in the latest computers and the latest browsers, and if you take it over, you win the computer in eternal glory, and people bring their best exploits there. And Vista first introduced this in Microsoft, and that year they could not take over Vista at all. It sat there unexploited for like 2 days until they went back to XP and people could take over XP. But this befuddled all the good guys. They could not find a way in to get around this defense for a while. And when we were just talking about with the NX bit implemented at the motherboard, you can mark this part of memory non-executable. It's only supposed to contain variables like names and addresses. It's not supposed to contain any exploitable code. So if you mark this area non-executable, and yet the programmer makes a mistake in C, and you're able to overflow with buffer and change this number, you can change it, and it will try to return, and it will go here, but it will not execute even the NOP. It will stop immediately and say, attempt to execute non-executable memory, I quit. And the combination of this and ASLR is what made Vista last an extra year before people found out how to overcome these defenses, and that raised the bar. a whole generation of old malware will no longer run on the modern operating systems because of these defenses, and the attacks have to get more sophisticated to overcome these problems. And that's all you ever get. There's no perfect defense, there's no perfect attack. It's just every time you put up a defense, it takes a while for the bad guys to figure out how to overcome it, and now their attacks are more difficult, but they get back in. Yeah?
Why do you need all the knobs? Why don't you just put the egg?
If you could exactly predict the location, you could just put in the egg. The reason you put in the knobs is to give yourself some ability to handle unexpected errors. And all of your attempt to find out where your code is going is pretty imprecise. In fact, I should mention, since you brought it up, the way you overcome this one, the fastest way people learn how to do this is with a heap spray. A heap spray works like this. You make your attack with a really big knob sled, like 10,000 bytes and 100 bytes of egg, and then you just run JavaScript and you fill the entire RAM with your attack. Then you just jump at random. And you're probably going to hit one of those knobs and take over. Now it doesn't matter where you were in memory because you fill everything with your attack. That's one simple way to do it. Anyway, another defense is a canary, also implemented in all modern operating systems. So when you make a stack frame, you're in the main routine and you call this subroutine. When you make a new stack frame, you put a random canary value here and you store another copy of it somewhere. So now when you try to return, you're done processing this and you want to go home, like I say, this EIP should really be down there. I wrote this before I taught the exploit development class and didn't have all the details right. But the canary value is here, and before it uses this value, it checks to make sure this has not changed. And if it has changed, it will stop. That's what stack smashing detected is. That's what happened to me in this case. It detected that I ran out of the name and changed areas I shouldn't have been able to change, and therefore it stopped execution because the canary had been changed. It's named after a canary in a coal mine. Miners used to have a canary in a cage on a stick, and they would put it in there to see if the air was poisoned. Because the canary was apparently very sensitive and would pass out at a level the humans wouldn't notice yet. And so this will tell you if somebody has done an overflow, and then you no longer trust that value. So in the capture the flags, there are various exploits where you have to figure out how to overcome this. I remember one of them taught me about 64-bit processors. 64-bit processors have more registers and they have special floating point registers. And there was a capture the flag I did a year or two ago where they were putting the canary value in the floating point registers, which I didn't even know existed. And you had to learn what they were and figure out how to get it out of there to store the canary value. Because if the canary is not random, or if you can find where they're hiding it, you can craft your exploit to put that value back here, so you will not get detected by this. And that's what you had to do to take over that one. All right, so I got a few eye clickers. Come grab one if you need one. Like I say, that's why you should be doing capture the flags. They will move you beyond these classes into the real current stuff that is really happening out there. Sheet at 123, 311. No good?
Yeah.
Let me see.
Low battery.
Okay, well, I gotta fix it. Oh, it's probably all right. It's just telling you it's not listening.
Oh, okay.
I think it's okay.
Oh, yeah.
Take another one if you like, but I'll put that one back because it's normal that it blinks those lights right now when it's not listening. All right. So, there you go. So what are the essential parts of every programming language? I guess I can quit at 25. Looks like the answers are coming in. All right, of course you need branching, looping, and testing. Otherwise you don't have a programming language, you've got something else, like perhaps a markup language. It might be useful, but you can't really do programming in it. You cannot solve all the problems that have clear algorithms. All right, what's the binary language built into the microprocessor? that's machine language. It's built into the processor by the arrangement of silicon when it's built. And by the way, here's a fun fact. The Pentium 4 processor has 100 bugs in the machine code. You can never fix them. You can't patch them. You can put firmware around them to try to dodge them. And the U.S. military, the U.S. government, I think about 3 years ago, they told us to quit using products from Huawei in China. The problem is when you use chips from another country, they could put hardware Trojans in the chip. It could have an extra function in there that you don't know about, and there is no way to audit the hardware. You'd have to like take an electron microscope and dissolve it with acid and check all the little pins and wires and connections inside there and somehow know if one of them is wrong, and that's like a moonshot worth of work. So they are very, very worried about hardware Trojans in devices, and the NSA will do that. That came out with the Snowden revelations. If you are a targeted company and you order a Cisco router, they will intercept it at UPS, take it out, put in more chips, so like put a bug in it, and then ship it to you. So you get devices with unexpected hardware in there, and that's very hard to detect, very hard to stop. Yeah?
Is that what they have now in Samsung Smart TV?
Well, the Samsung Smart TV was a software exploit. But by adding hardware, they could of course do that anytime. They could just go in your house and put a bug on the wall or in the TV or anywhere. But if they can do it with software, then it becomes practical to do it to a million people. That's why, if you talk about how no defense will really stop the NSA, but the point is if everybody used encrypted telephone calls, for example, it wouldn't stop them, but it would make it much more expensive to tap each phone. So it would no longer be financially possible to tap all the phones in the country. They'd have to only tap the targeted ones. Anyway, but that's the issue. There are bugs that can't be fixed. And with embedded devices and Internet of Things, we have more and more gadgets with bugs that cannot be fixed. Because, for example, the manufacturer just doesn't know enough and they don't provide an update, and they didn't think about building an update mechanism into like a stuffed toy. So there's actually no way to fix it. And that's why the only way you can defend Internet of Things and other vulnerable objects is the same way you defend children that are vulnerable and you can't patch them. You protect them from the outside. You have to have firewalls and intrusion detection system and network segmentation that limits who gets close to the vulnerable thing. Since the vulnerable thing can't stop being vulnerable, you have to put defenses on the outside. Anyway, all right. So which of these codes put comments in your C? Test this one. Looks okay. All right. So that is D. Good. Okay. This turns out to be super important in SQL injection. In SQL injection, you often inject code and then you have to have a comment symbol at the end. And I was very frustrated when I started doing SQL injection because I would use a dash dash, which only works on Microsoft SQL. And I learned to try like 4 different kinds of comment statements at the end. You have to find the appropriate one for whatever language is on the server. Anyway. All right. Which one is required in every C program? Quit at 25. All right, you have to have main. This, by the way, is a big difference between programs and libraries. If you write a program, it has only one place where it starts, and that's main. A library has many entry points. You might want to call this function or that function or that function. So if you go into the world of Windows, libraries have many exports. Executable code only has one export, main, which is how you should come in. Anyway, so which one of these puts library code in C programs? I'll quit at 25. All right, and that's include, which includes other code from a library. So now you're not in control of your security anymore. You're trusting someone else. This is like outsourcing part of your company to a foreign contractor. Now you're not really in control of what they do anymore. but you also don't have to do the work, and it's possible that they do better work or worse work than your staff. We had a huge argument at the college when I wanted to move our student email to Gmail, and other people wanted to keep running our own email server. The argument is, you lose control, but are they smarter than you? Are they doing a better job than you? And you have to debate all this. Anyway, so we're at 10:05. Let's take a break till 10:15, then we'll carry on. I'm gonna stop this recording, which is this thing, chapter 7.